Hello, in this video I'm going to solve question number 7 from problem set 1. Let us review the question together first. Let capital X be a set and let little d be a metric on X. Show that the function capital D defined from the Cartesian product of X with itself to the set of real numbers R defined by this relation is a metric on X. The relation is that capital D of X and Y is equal to the minimum of these two numbers. Number 1 on the one hand and the output of little d of X and Y on the other hand. Okay, in order to show that capital D is indeed a metric, I need to show that capital D satisfies the properties that we expect from a metric. The first thing is to show that for all choices of X and Y in the set capital X, the output of the capital D acting on X and Y is a non-negative number. So that is what I want to convince myself of. Let me just do it orally. So d of X and Y is the minimum of these two values. Of course, this value is a positive value, and because little d is a metric on the set X, we don't know exactly what this number is, but we know that the value is at least equal to 0. Okay, so you have number 1 on the one hand, and you have a number that you are guaranteed to be non-negative on the other hand, and then you want to take the minimum value of these two numbers. Okay, definitely it becomes a non-negative number. Yes, if dx and y is less than or equal to 1, then the output of capital D is indeed little d of X and Y. And if d of X and Y is greater than 1, then the output, then in that case the minimum becomes 1 and the output is actually 1. So in any case, this is actually guaranteed to be true. Of course, you need to write it in written form if you want to do it in a written form. Okay, now the second part is I want to show that this is actually the case that for all X and Y in X, we want to show that capital D of X and Y is equal to 0 if and only if X is equal to Y. Okay, let me start from this side. For example, let us assume that X is equal to Y. And I want to show that the capital D acting on X and Y gives me indeed 0. So what happens? If X is equal to Y, because little d is a metric, it is guaranteed that dx and y is 0. Okay? And then capital dx and y in this case, according to the definition, is the minimum of dx and y and 1. But if x is equal to y, this d is 0, so this becomes minimum of these two numbers, 0 on the one hand and 1 on the other hand. But you know that the minimum of this set is 0. So we were able to show that if x is equal to y, capital D acting on x and y gives me 0. Okay, I need to convince myself the other way around, so I want to prove this direction. This time I know that capital D acting on x and y is 0. I want to show that this is the case, that x is equal to y. Okay, so you are telling me that capital D acting on x and y gives me 0. I know that capital D acting on x and y is the minimum of little d acting on x and y and 1. Okay, this is equal to 0. We know that. Okay, so now I'm claiming that this number should be 0, because if this number is non-zero, then I have two non-zero numbers, and definitely the minimum of these two non-zero numbers is a non-zero number as well. So if the minimum of a set consisting of two numbers, one of which is non-zero, is equal to 0, there is no way unless the first one is 0. Yes, and because little d is a metric, I can conclude that x is equal to y. So we realize that this is true for all choices of x and y in the set X. Okay, number 3 is symmetric property. So we need to show that for all x and y in X, then capital D acting on y and x is equal to the capital D acting on x and y. But this is so obvious that I don't want to continue here for you, because if you want to write that, so if you want to write it, of course, dy and x is actually the minimum of little d of y and x and 1. But you know that because little d is a metric, it is symmetric, so there is no difference between dy and x and dx and y and 1. And this is exactly the definition of capital D acting on x and y. So this is it. So the important property that we need to check is the triangle property, triangle inequality. So let me do it on the other page. Okay, to do it a little bit simpler, let me state a lemma here. A lemma is a true statement that I can use it to prove my main claim, my main theorem. Okay, so I would say let A greater than or equal to 0, B greater than or equal to 0, and C greater than 0 be real numbers. Then the minimum of A plus B and C is less than or equal to the minimum of A and C plus the minimum of B and C. So this is what we want to prove. So let us try to prove this lemma first, and then of course this will help me to prove the triangle inequality for capital D. Okay, how can I prove this? We can consider some cases. Okay, let us say that A plus B is less than or equal to 0, because for A, B, and C, I have 3 possibilities. Either A plus B is less than C or equal to C, or A plus B is greater than C. These are the possibilities that I can have. And let me also write here, this is or, okay? Okay, in the case that A plus B is less than or equal to C, then the left-hand side of the inequality becomes just simply A plus B. Yes, because if A plus B is guaranteed to be less than or equal to C, if I ask you what is the minimum of this set, of course this is A plus B. But because A and B are considered to be non-negatives, non-negative real numbers, if this is the case, I can conclude that A is itself is less than or equal to C. Because A plus a non-negative number is less than or equal to C, then it is guaranteed that A itself is also less than or equal to C. In that case, if I ask you what is the minimum of A and C, the answer is simply A. And of course, for the same reason, B is also less than or equal to C. And if I ask you what is the minimum of B and C, then you will tell me this is B. And then the right-hand side becomes equal A plus B. Okay? So if this is going to happen, the left-hand side is equal to A plus B, and the right-hand side is equal to A plus B, and then it means that the left-hand side is indeed equal to the right-hand side, and of course it means that the left-hand side is less than or equal to the right-hand side as well. Okay, so in one case I was able to show that the left-hand side is indeed less than or equal to the right-hand side. But what happens if I have the other scenario? What happens if I have A plus B greater than C? In that case, the left-hand side becomes just simply C. because I'm assuming that C is less than A plus B. So if I ask what is the minimum between these two numbers, you show me C. So the left hand side in this case is C. But let us look in the right hand side. So what are the possibilities for the right hand side? Yes, let me just write them with a different color. So here we might have C and C. Yes, it might happen that the minimum of A plus C is C, minimum of A and C is C, and minimum of B and C is C. This happens if C is smaller than A and smaller than B. Remember, I'm assuming that A plus B is greater than C. Of course, in that case, the right-hand side becomes 2C, the left-hand side is C, so the left-hand side is indeed less than the right-hand side. Okay, so in other words, I'm considering cases. And then another case is that this becomes, for example, A, but this remains C. This happens in the case that the minimum between these two numbers is A. It means that A is smaller than C, but C is smaller than B. In that case, the right-hand side becomes A plus C. But A plus C is also greater than or equal to C because A is a non-negative number. So again, the left-hand side is less than or equal to the right-hand side. Another possibility is that this is C, this is B. When this happens when between A and C the minimum is C, and between B and C the minimum is B. But again, this right-hand side is the sum of these two numbers, and C plus B is again greater than or equal to C because I am assuming that B is non-negative. So you see that for these three possibilities, the right-hand side is either 2C or A plus C or C plus B. In all these cases, the right-hand side is greater than or equal to the left-hand side because the left-hand side is just simply C in this case. The only thing that we need to be careful about is that what happens if this becomes A and this becomes B. Yes, when this happens, it happens when between A and C the minimum is A, and between B and C the minimum is B. In that case, the right-hand side becomes simply A plus B. And of course, again, A plus B is greater than C. Why? Because I myself is assuming that. I am assuming that A plus B is greater than C. So you see that in all cases that I have, in this case, the right-hand side is simply 2C. In this case, the right-hand side is simply A plus C. In this case, the right-hand side is C plus B. And in this case, the right-hand side is A plus B. Okay? And in all these cases, the left-hand side is just simply C. So if this happens, I am done. If this happens, I am done. If this happens, I am done. And even if this happens, I am done because I am myself assuming that A plus B is greater than C. Why? Because if A plus B is less than or equal to C, I have already the proof that this left-hand side is less than or equal to the right-hand side. So this means that in any case, this inequality is satisfied. So remember my conditions. A and B that appear in this inequality are non-negative real numbers, but this number C that appear is a positive real number. Under these conditions, I was able to show that this is indeed the case. Now let us go back to the triangle inequality for capital D. So I would say that let x, y, and z be arbitrary elements of the capital X. We show that capital D of x and z is less than or equal to capital D of x and y plus capital D of y and z. How can I do that? Okay. So let me just rewrite them in the language of the problem. So instead of capital D of x and z, I can use this relation and translate it here. So, but this inequality, so let me put this one, this inequality is equivalent to what I am writing here from the left hand side. This is minimum of little d x and z and then plus and 1, sorry, is less than or equal to, okay, let me write it in this way. So let me start from here. We know that the minimum of this is smaller than or equal to the minimum of dx and y plus dy and z and 1. Why is that? I am telling you that the minimum of this set is less than or equal to the minimum of this set. Why is this? Because this one and that one are the same, and because little d itself is a metric, we know that this number here is less than or equal to this number. Okay? So I have a set consisting of two elements. One of them is this number, the other one is 1. Here I have also a set consisting of two elements from which one of them is the same number 1 and the other one here is greater than or equal to that number because little d is a metric. Then it is guaranteed that the minimum of these two numbers is less than or equal to the minimum of these two numbers. But now look, here I want to give the role of little a to this number. I want to give from the lemma, give the role of little b to this number and give the role of c to this number. Are they satisfying my conditions? Yes, because d is a metric, its output is a non-negative number, so it is guaranteed that a is non-negative, b for the same reason as non-negative, and you see that 1 is strictly positive. So these a, b, and c that I introduced here satisfies the condition of my lemma, so I can use my lemma. So what is my lemma? This tells me that this is less than or equal of minimum of dx and y and 1 plus the minimum of dy and z and 1. Yes, but if I ask you what can I write instead of that based on the definition of capital D, I can write it as d of x and y. And if I ask you what can I write for the second term, hopefully you agree with me that this is nothing except capital D of y and z. So where did I start it here? If I ask you what is this that I have written here, this is just d of x and z. So I would say that dx and z is equal to this, and this one is less than or equal to this expression. So I was able to show that this expression is less than or equal to this expression. Okay, so this finalizes the proof that capital D is also indeed a metric if a small d is already a metric on the set X. Okay, so I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.